All right, guys, welcome back to another episode of Introduction to Computer Networks. This is Polly streaming from NTU. All right, let's check out what's new this week. Okay, this is W13, meaning we have just 3 weeks left after this week, okay, for the semester. Let's see. Oh, you are seeing a long list of assignments that would be due this Saturday. All right, guys. Yeah, you want to be a little bit anxious, but not overly anxious, okay? And hi, Josh. Hi, Nitro. Nitro equal Nicholas, I suppose. And Zach. Hey, welcome. First is PA8. Okay, guys. So this is the third hardest PA. So if you have not yet started it, definitely started it today, okay? Or get your teammate who's the best, okay, doing the Golang programming to do this. Yeah, and hey, Miguel and Justin. So PAA is due this Saturday, all right? And the good news is that I think, 6 of the teams have already submitted PA and PA8 and passed PAA. And to my surprise, 4 of the teams have already passed PA9. Okay, so I guess some of you got a hang of Golang programming already by now and having fun doing the PAs. Now, let's see. We do have 7 quizzes due this week, but no worries. All 7 quizzes are straightforward, all right? So I think at least 4 of the quizzes are actually to encourage interactions, to communicate the spirit of a routing algorithm, which is really odd, okay? It's not very intuitive, okay? So 4 of the quizzes are here to help you understand, to get an intuition of that routing algorithm, okay? So that's this week. Let's check out the topics. First, IPv6, we are not quite yet done. So this is just a very short video, 1.5 minutes, talking about how we are adopting IPv6 into this IPv4 world. Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, please don't. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Okay. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings. Okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app? Yeah, so why is it so hard to adopt IPv6? Polly used to have a quiz trying to make a point. It is not easy to make a change a lot of times. But you know what? This semester, I'm going to use this. Guys, check this out. Right? In the video, Polly talked about statistics from Google, but that was a few years ago. So the adoption rate is only 8%. But hey, check out, what is the adoption rate now? So by November 19, 2023, you see that the adoption rate is 43.51%. So this is much better now. So after a few years, we're seeing a significant growth, okay? And it seems that people are more aware and looking to IPv4, pure IPv4 internet. So the adoption rate is actually picking up, okay? Good news. And with that said, we move on to the next topic, and this is the beginning of the modern forwarding. Before generalized forwarding, all we've talked about, IPv4, IPv6, forwarding based on destination address, these are all the traditional forwarding. Okay? And modern forwarding is generalized. So in this overview video, okay, you will get a rough picture of how generalized forwarding works. Okay? It's a little bit long, 5 minutes, but very crucial. Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. If we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. So in the traditional forwarding, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now if you recall the overview of chapters 4, you should recognize in SDN, the control plane look very different. Instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. Okay, this is similar to traditional routing, right? In the control plane of the traditional routing algorithm finished computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing, very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables, but in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so the flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple, matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, SDN is actually referring to each of these entries, each of these rows in the table. That is also saying if packets coming into this router, okay, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. Okay, so we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, okay, and then determine it should go out on interface 2, arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, okay, matching the destination and source address. So in the header column, okay, of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry, and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. Okay, so matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. Okay, for this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. Okay, so you see, header column here for matching purpose, last column here for action purpose, and counter here for management purpose. All right, so that is the overview. And a key message in this video is that in traditional forwarding, we use a forwarding table because all the actions we take is just to forward. But in modern or generalized forwarding, we call this table the flow table. And that is because it's not just forwarding we can actually drop a packet. There are actually a variety of actions we can do. These will be coming up in the next videos. Another thing is that we will not be only matching the destination address. So we now call each of these entries in the flow table a flow entry. Okay. Now, the next video is to talk or to give more specific fields we see in a flow entry. But let me come back to the question during the video. So Justin was asking, is the recent increase in adoption rate due to the increase of internet-capable devices? Okay, as if IPs are a depletable resource and IPv4 are running out. Yeah, so obviously there is a higher demand of connecting to the internet. Okay, that is, I think, partly the reason that adoption rate is increasing fast recently. I think another is that IPv6, although the IP address space is longer, but the header is actually more compact, meaning the overall overhead of sending IPv4 packets is still better than overall overhead of sending IPv6 packets is still relatively lower than IPv4. So in a way that it's a more efficient protocol as well. And I think a final reason is that the internet infrastructure or the bodies that manage the internet infrastructures in each country is more aware of the need. Okay, so they are also promoting strongly of the machines, okay, and devices or routers migrating to IPv6. I would say that, yeah, it's a multi-factor. All right, so that answered the question. Next, okay, this is to introduce the flow entries a little bit more in detail. To put in simpler words, we take a combination of these header fields with specific values, and we define that as a pattern, okay, for a flow. So whenever there's a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table. Some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries, and each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority? Therefore, we take the action, okay, in the prioritized entry. Okay, so priority there is to disambiguate all the matching entries. Now, in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do what? Prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. Then, you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the lengths to break the tie. So we have a specific priority field there to break the tie. Okay, so the forward table in a router, 4-column, and it defines how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, we don't want to match the source address being 1.2. something. Okay, so the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then it doesn't matter what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4. something, and then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples, you get a rough feeling. Now, let me come back here. I have not yet explained what open flow means. This is the data plane abstraction for SDN routers, all right. Okay, what does open flow mean? Open flow, capital O, capital F. It's a very specific term. It is the protocol defined for communication between the data plane router to the control plane remote controller. So the remote controller installing forwarding table using the open flow protocol. All right, so the key message in this video is this. You see that the matching rules, more general. You see that the actions, more general. Now you see a variety of actions in the video. There's also something, priority, which is also more general or specific. In traditional forwarding, we could have multiple matching entries, right? And how do we break the tie? We actually take the one with the longest prefix. But in modern forwarding or generalized forwarding with the SDN, we can actually specify priority to each of the flow entries. All right, so also more general. All right, so next video is to introduce the flow table a little bit more formally, and you will see how diverse the matching rules can be. It can use the header fields it can use the fields in the IP header. It can also use fields in the link layer header, as low as link layer. With the generalized forwarding explained, now let's go back to this notion, the flow table. This is one of the most important things in SDN's data plane. Recall early slide. Flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column, priority, and we just ignore that here, as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters, we know, one counting bytes and one counting packets. Action column, 4 classes of actions. One can forward a packet to an outgoing interface, one can forward a packet to the remote controller.
One can drop a packet as an action. One can also change the content of the packet as an action as well. So all these straightforward. Now, this column here, very complex. Okay. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, in the early side is also called a header column. The reason it's called the header column is we're using the header fields essentially to compose these rules. In the three examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. One can use other fields in the network layer header for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets coming into the router through a particular incoming port. So that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. So that's also why in this slide we refrain from calling this column the header column, because we do have a field that's not necessarily a packet header. So we call them rules in general.
All right, so that is the full flow table entry definition. Next is let's check out a few examples of defining specific rules. And you will see that we could actually define rules not only to forward, but to drop packets like a firewall. Okay, so here are the examples.
Let's take a look at how diverse these rules can be, again through a number of examples. First is the destination-based forwarding. Now this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8. Now we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. The second and the third example are there to serve security purpose, to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet definitely something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? A mean or a root username, and guessing the passwords for the root or a mean. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. Okay? So blocking packets to port 22 is to block any logging request to port 22. Therefore, SSH is disabled on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack. DOS attack, denial of service attack. You see, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share IP addresses of zombie machines. So if one day a hacker hacks through the workstation and take over the workstation, 140.112.42.161 is going to be a zombie IP address. So the experience system admin, okay, after looking up the website displaying all these zombie IP addresses, can set up these entries, okay, with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in, okay, and asks all the zombie machines to issue, for example, login requests, okay, then our machine is gonna under attack. So experience admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH, brute force attack. Yeah, guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So with this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch, okay, or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch, we need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. Okay, so that is the use of the switch there. So you see why. This entry here is looking at the destination address at the link layer. That is also called the MAC address, and it looks very different from the IP address. So if this packet comes in matching this link layer address, then that's forwarded to output port 3. Right? So that is
so that is the 4th example. And it takes us to the quiz today. Okay, so the first one is called the SDN flows. So what you're seeing are 2 more entries in the flow table. The first entry says this: if I get a packet from 10.0.0.1 and source port number 52391, this SDN router is going to take these 2 actions. First is to change the IP source address to this new one, 42.161, and change the source port number to 11999. Okay, so originally 10.0.01 changed to 140.112.42.161. Originally port number 52391 and changed to 11999. But in the second entry, if I get a packet saying the destination address is 42.161 and the destination port number is 11999, then I take these 2 other actions. I change the destination address to 10.0.0.1. Hey, that's what the original source IP address is, right? And the D port back to 52391. So guys, what are these 2 entries for? What are these 2 entries for? Okay, so let's go to the score space. I see already students typing up solution. Oh, too fast. Okay, yeah, I guess it's very intuitive, right? Yeah, it's NAT, isn't it? So the first entry is to allow the packets from the local area network to go out. And the second entry, right, is to map the destination address back to the local address and the destination port number back to the local port number. All right, very good. Yeah. So, great job. Jeremy, hey, number 1. And Isa, great. Good. And by the way, this one is very intuitive. We'll not take a fast responder for bonus. Everyone gets a bonus. Okay, so this is one of the quizzes to encourage interaction. Okay, so this is also to show that, guys, you probably don't need to memorize things all that much. if you just follow examples we talked about in the video, it's not that hard, right? You come up with what a couple new entries are for. All right, great. Let's see. Yeah. Sophia, it is Nat, right? Tao, it is Nat. Anthony, Nat, obvious, right? Justin, Kaze or Jintao, Nicholas, Nat. Okay, great. So you guys got an idea. And we can move on to the next video. Okay, so in this video, you will hear in the first part, Polly summarizing this thing, that you probably get a rough idea already that these SDN routers can be very general, right? They can be configured to work like a traditional router that does forwarding based on destination address. It can be configured to work like a NAT box. It can be configured to work like a firewall. Yeah, there are actually a variety of these devices we're using today that can be easily emulated with proper configuration on these SDN boxes. Okay, so this is the first part of video, and later on you will see in the second half of the video, SDN is very often used by for example, a corporate network, an institutional network. Inside such a network, there could be subnets. And these subnets are connected through SDN routers. And you have a controller doing the route computation. And then you use OpenFlow to install these flow tables into each of these routers. So in SDN routing, SDN forwarding, it's very centralized control. Okay? And these tables, in the flow tables of each router, you will see some entries that will enable packets to flow one direction or another. And it can be very policy based. Instead of using a shortest path algorithm, which you guys will learn tomorrow. All right, so this video, somewhat important. And quiz number 38 will follow right away. And for quiz number 38, Polly will take the first responder. Okay, so this is just to prepare you. Okay, and this video, also about 4.5 minutes.
With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing the packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN, okay, is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. So you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the OpenFlow protocol. Right? So this controller here, sometimes being also called the OpenFlow controller. Just like the SDN routers, okay, some of them will actually call them the OpenFlow routers. The scenario is this: let's send packets from H5 and H6 here and here, okay, from subnet 10.3 to H3 and H4, H3, H4, subnet 10.2, okay, but through a very specific route, okay, from S3 here through S1 and then reaching S2. So yeah, we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this, okay, if you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hop, okay, this is the shortest path. Traditional routing does not provide you the flexibility of manually configure a specific route. But hey, luckily we have the OpenFlow controller. So OpenFlow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, S2. And these entries will look like this. Okay, inside S3, the flow entry will look like this, source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now, the entry in S1, this router at the bottom, will look like this. If the increased port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 flow entry looking like this. Increased port being 2. So packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So there I got this one. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So OpenFlow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? The controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing.
Yeah, and that takes us to quiz 38. Sophia, I'll come back to your question after we're done with quiz 38. So, hey, here's OpenFlow for a whole network. And this is the exact example you saw from the video. So Q1, I suppose, will be trivial. If you follow the video, you will know which way the traffic will go from H5 to H4. H5 is right here. H4 is right here, right? Is it A, B, C, or directly AC? Now, I guess the tricky one is Q2. Suppose H4 will be sending traffic back to H5. So H4 sending traffic back to H5 and through B. So if H4 to H5 traffic should go this way, CBA. How would you change these tables in router C, router B, and router A? Okay, I think adding entries to them so that these routers will be forwarding the packets from H4 to H5 accordingly. All right, let's go to the score. Channel W13, quiz 38. Okay, guys, fast responder gets bonus. Okay, and you guys have 5 minutes. Okay, let's start counting time. Great job, guys. Let's see. The first responder is Team 1. Team 1 says the path for H5 to reach H4 is ABC. Yeah, so this one is trivial. Okay, so what's a little bit tricky is Q2. So I guess what Anthony here meant is router C, we add an entry. If the source equals 10.2.2.1, which is the IP address of H5, right? Oh, sorry, H4. If it's coming from H4, router C will forward it through interface 2. And that is, I think, to the left, towards B. Good, makes sense. And in B, we add another entry. If the ingress port is 4, which is the interface taking packets from the right, and the source is H4's IP address, destination is H5's IP address, forwarded through interface 1, which is sending packets upwards. Yeah, sounds good. And then A adds an entry, which is what? H4 to H5, right? The matching rules, source being H4, destination being H5. There, you're getting a hang of writing a flow table entry. And what is the action? Forward to 2. Okay, so you guys do have the ability to try to, follow examples and create entries for your purpose. All right, so sounds good. But maybe this guy here is, this entry is a little bit too restrictive, because in case H3 is sending packets to H5, then it is also enforced. Okay, wait. Oh, no. This entry meant actually all packets coming from H4 will go to interface 2. Okay, so there's no way packets coming from 10.2.2.1 going directly to subnet A. But we see in Team 4 here, yeah, it's very consistent, matching source and destination IP address and action forward to. Matching source and destination address and forward 1. Right? Matching source and destination IP address and forward 2. Let me see. I guess this might be a bit restricted, but in this scenario, it might still be okay. Let's see. Team 3 is the third fastest. Source, okay, wild card. So as long as it's coming from C subnet, then forward the data to 2, then this one is very restrictive, right? If H3 is sending, it would definitely also go to the left to subnet B. Interesting. Subnet B says if the source is from subnet C, just forward it to 1. Yeah. And for subnet A's router, if it's coming from port 3, forward it to 2. Of course, this will also work. Yeah. But this, in case there are traffic also coming from B, from, for example, H2, and it's supposed to reach H6, it would actually go to H5. All right. Yeah, isn't it interesting configuring these SDN flow tables? So sometimes you need to be careful about the granularity of your specification. Okay, let's see. Okay, hey, Team 5 specification is very, very restrictive. Yeah. Yeah, because the ingress port sometimes also limit the direction of the packets. And I think this will also work. Great. Yeah, I see you guys all have a hang of these. Yeah, configuring SDN routers or flow tables. And you know what? Let me just also point out something. Yeah, this controller on the upper right so it's a kind of grayed out. One can actually do manual configuration and then have the controller using the OpenFlow protocol to install these manual configure routes into router ABC. Yeah. And now let me come back to the question from Sophia. So it might be a naive question, but what happens if one of the routers fails? I can't help but think that this might be a big drawback for a centralized system. This is a very, very interesting question. I would say, Sophia, I agree with you. I would also be anxious, right, if one of the routers fail. But I'm not sure, though, whether this is specifically the drawback of a centralized system. Usually in a centralized system, there's a central machine overlooking everything. Very often it detects problem a little bit earlier because the control is centralized. In a way, there are these debugging messages or management messages that are sent back to the controller here. So that upper right controller box there gets all kinds of debugging messages from router ABC. It might be easier to detect failures this way. And being centralized, the benefit is also that, hey, if router B failed, from the controller, just quickly reboot and reconfigure. If you use a decentralized algorithm to control all these routers, and if they work kind of a distributed way, it might take some time for the system to finally converge to the true picture of the network. Yeah. So Sophia, I know it's a little bit counterintuitive, but tomorrow you will hear two routing algorithms. One is a little bit more centralized, the other is more decentralized. Okay, and I think next week we'll talk more about these. I will ask you again whether you will prefer the centralized or decentralized in case there are failures. All right. It will just fail if the destination is offline. Okay, I guess this is to address Oh Yang's question. If you want to type, use. Oh, okay. Okay. Yeah, so Oh Yang is trying to offer help to type things up on Discord. I think Mikhail is trying to help Sophia, right? Oh, okay. Okay, so \* is an escape so that you can show more stars. Okay. Oh, Yang, thank you. Thank you. All right, and you know what? Yeah, so Miguel is trying to help Sophia. In a centralized system, by the way, generally speaking, it's actually easier and faster to make changes in a centralized system. Yeah. All right. Well, you guys will hear more. So tomorrow, we'll start the next chapter, chapter 5. It's the control plane of the network layer. All right. So with that said, definitely come by tomorrow morning. And this is all we have today. Goodbye. See you tomorrow. Okay, bye. Mhm.